In this video, we're covering lesson number 2 from the first week of unit number 4 in calculus class. We're going to take a step aside from computing related rates and talk a little bit about function behavior, and then as we revisit related rates a little bit later this week, we'll see them in the context of optimization. And it's the combination of related rates and graph behavior in which we can use to find the optimal values in a particular situation. So just some questions to get us started thinking about graph behavior here. We've got the function y equals x squared on the domain negative infinity to positive infinity. And so if you recall, this domain is what we call a domain with interval notation. And a lot of times I prefer to see this notation, x element of the domain from negative infinity to positive infinity, and that way there's no confusion. We're not trying to talk about a coordinate here, we're talking about all of the x values that exist between negative infinity and positive infinity. So we are implying that this graph does continue upward and outward forever. So where is the minimum point? You can probably spot it pretty easily here. It's right there at the bottom of this curve. Minimum point occurs at 0, 0. And where is the maximum point? Well, since this function increases towards infinity and there's no boundary on this graph whatsoever, we would say that there are no maximum points. There are none, since y increases indefinitely. Now if we jump over to the side here, we see the same equation, y equals x squared, but this time we're talking about on the interval from 0 to 2. So all x values between 0 and 2 inclusive. So we include the point at 0 and the point at 2 on the x-axis. So in this little section here, where is the minimum point? Well, that occurs at the same spot, 0, 0. The minimum point, of course, being the lowest point in the graph, the lowest value associated with the y-axis. Now, unlike the last example, we do have an endpoint to this particular function. It does not continue indefinitely. The domain of the function, or the domain of this particular example, limits the function growth, and when x equals 2, the function stops. So therefore, there is an upper limit, if you will. There's an upper boundary to this function's position, so we can say that there is a maximum point, and it does occur at 2, 4. And one more time, if we use the same equation, but this time adjust the boundary, this time from 0 to 2, but 0 is not included, where is the minimum point? This time we would say there is no minimum point. And we would say that that's the case here because the function values, the y values, tend towards 0. If we were talking about limits, we would say that the limit is equal to 0, but the function value itself is tending towards 0, but it never quite reaches 0. So no matter how close of a point we choose, and if I could zoom in infinitely, I would, no matter how close of a point we choose, we can always find another point that's a little bit lower. And that's the case because the final position, 0, 0, is not a part of the domain of this particular function. We do have a maximum point, and it's the same as the last example at 2, 4. And I'm sure you can figure out what's happening here. We have another copy of the same function. This time the boundaries are not included, 0 and 2. So where is the maximum and where is the minimum point? And for the same reasons as discussed before, there is neither a maximum or a minimum point. So if I were to summarize what's happening in these first 4 examples, let's just kind of point out that maximum and minimum points will occur as long as there is a boundary or an endpoint on either side of the function. Now, even if that function does do some radical things, if it snakes around all over the place, as long as there are endpoints somewhere between those two defined endpoints, we will encounter a maximum and a minimum value. If those endpoints are unbounded, or if the function itself is unbounded, then we will not encounter, or will not necessarily encounter, maximum and minimum points. And here's a weird example to consider. Where's the minimum point of this particular function? Well, this function is a piecewise function, and it's defined with these two expressions. If we're looking at the graph, it appears that there are two positions that contain the lowest y value of the graph, and so therefore we would say that there are two minimum points. We have one at 0, 0, and again one at 1, 0. And that's okay. We can have two minimum points as long as their y coordinates are the same and these y coordinates are the lowest y values in the entire graph. When it comes to the maximum point, however, again, this function has a series of values that are increasing. They continue to increase all the way up towards this point. But since this point is undefined, and we could again theoretically continue to pick more and more x values that produce larger and larger y values, we will never actually reach the largest y value. So there are no maximum points here. And we do have a function. It is bounded on either side, left and right, but this portion of the graph in the center is unbounded. And so on the entire interval, we can't say that there's a maximum point. But maybe if we were to input, or if we had a similar function, but we put an upper boundary right here at 3/4, if we had an upper boundary or an upper limit on the function itself, then we would be able to find a maximum within this particular portion of the graph. But as we consider it in its entirety, there is no maximum value. And lastly, we don't have the equation that produces this pair of shapes, but clearly it would be some sort of piecewise function. If we were to identify the minimum point, well, I think that's going to occur right here. This position produces the smallest y coordinate. Now, I don't even have numerical values for this coordinate, but I do know that it would occur at whatever the x value is at this position A, and whatever the y value is at, or based on that x position of A. So by being very general about it, we say the minimum point occurs at A, comma, f of A. As far as our maximum point goes, well, we've seen this before. This function is approaching some position, but because of the undefined point right there, there is no maximum point. There's always going to be one y value larger than the last, so we would again say that there is no maximum point here. Now, I've mentioned it before that in higher level mathematics we like to rely on definitions in order to make claims about the things in which we talk. And so here's the definition for absolute maximum and absolute minimum. We're going to say that some function f is defined on an interval I that contains some x value c. That's really what's being stated right here. We have a function named f, the interval called I, and within that interval is the number c. So if I were to use this diagram as an example, our interval I is the collection of x values that exist between A and B. So there's our interval, and we could pick some arbitrary location, let's say right here, and call that C. If we wanted to, we could call this position C and so on. C is somewhere in between A and B. That's what we mean by saying that the interval contains C. Now, if f of c is greater than f of x for every other x value in the interval, so if the y coordinate associated with the position c is bigger than the y coordinate for every other value, and I should say greater than or equal to, for every other value in that interval, then that function has an absolute maximum at that point c. So here's c again in that last example, and here's the position. So this y coordinate right here is f of c. Whatever the function calculated at c is, that's the y value. Now, if f of c, the y value, was bigger than every other y value between a and b, then we would know that c is the maximum point. But if I slide just a little bit over further to the right, here's a different x value, and I could calculate the y coordinate associated with it, and that would be represented by f of x. In this case, f of x is not less than f of c. F of c is not greater than or equal to f of x. So because f of c is not greater than f of x, we can't say that that's the maximum point. Similarly, if I claim that this position right here is the maximum point, we can call that f of c. But remember, if I slide just a little bit to the left of c to produce a new x value, then the function evaluated at x would be larger than c, and therefore it's not a maximum. Similarly, if I were to choose this particular point and call it c, which is allowed because the interval was all x values between a and b, so c is contained within that interval. C could be right here on the endpoint if we wanted to. The function evaluated at c is some number, and if I pick any other x value within this interval, any other position within this interval, and if I were to calculate the x value associated with any of those other positions, no matter how close I get, f of c will be less than or equal to, as described here, less than or equal to every other x value, f of x value, in that domain. So therefore, c would be identified as an absolute minimum. So that definition helps us with formal proofs and dialogue about extreme values. And it also leads us to this theorem here, the extreme value theorem. And this is also what I was mentioning just a moment ago, but a bit more eloquently, of course. A function that is continuous on a closed interval has an absolute maximum value and an absolute minimum value on that interval. So as long as we're dealing with a function that is continuous, here we are not dealing with a function that's continuous. Here we are not dealing with a function that's continuous. But if we are dealing with a function that is continuous and on a closed interval, this one's not a closed interval, so we can't use the extreme value here. We can't use it here either because the interval is not technically closed. But this one we can. We have a function defined on a closed interval. It's continuous on that interval. Therefore, there must be an absolute maximum and an absolute minimum. On this example here, we had an open interval, so that didn't count. But as long as we have a graph or a function on a closed interval, which means it has two endpoints that are included and is continuous in between, there will always be some absolute value, or I'm sorry, absolute maximum value and some absolute minimum value. So with that in mind, let's talk about example 1 from the textbook in a separate section. For the functions in the figure below, identify the location of the absolute maximum and absolute minimum value on the closed interval a to b. Do the functions meet the conditions of the EVT, or extreme value theorem? Well, the conditions on the EVT are that the interval is closed and the function is continuous on that closed interval. So in this first option here on the left, A, the interval is closed. Well, we were told that at the beginning. From A to B, the endpoints are included, so that part is true. And is the function continuous? So yes, that's true too. So the EVT states that there must be both a maximum and a minimum value in this group, or within this section. Sorry, I bumped the camera key there. I turned on my selfie cam. Anyway, yes, this function or this scenario does meet the conditions of the EVT, so therefore there is a maximum point and there is a minimum point on this interval. And again, we could say that the absolute maximum occurs at this point, even though the values for A are not clear, and then our absolute minimum occurs here at C, comma, f of C. In this particular example, the conditions for the EVT are not met. The interval is not really closed because of the opened endpoints on the left and the right-hand side, and there's also a point of discontinuity. So without this being continuous and without the bounded endpoints, this does not meet the EVT. Therefore, there's no guarantee of extreme values of a absolute maximum and absolute minimum. So again, that extreme value theorem just guarantees that it would be true if the conditions are met. Now, as it turns out, there is a data point right here that is the absolute value. I should say absolute maximum value. And for this particular position, f of c, the function evaluated at c, would be greater than any other function value in this range. Any other x value on either side of this section of the graph will produce a y value that's smaller than f of c. So because of that, we can say that there is an absolute maximum at c comma f of c. Now again, we weren't guaranteed that. The EVT would have guaranteed that, but even though it wasn't guaranteed, we did actually find one. Now, if we consider some slightly more complicated graphs, like this example here, this example does meet the conditions of the EVT. The function itself is continuous. I can draw the entire equation without picking up my pen or pencil. And the boundaries of the equation are closed. They are closed endpoints here, A and B. So the conditions are met. There must be an absolute maximum and an absolute minimum on this domain. Now, what's particularly interesting, and we've talked about this in class before, is that the absolute maximum and the absolute minimum must occur either where the derivative of the original function is equal to 0, or, and this is the new part, or at the endpoints of the graph, or when the derivative itself doesn't exist. And this is going to close that loophole for those non-polynomial functions for which we would need to find a maximum or a minimum point. So let's kind of just reiterate something here. This position does not have a derivative because of the cusp or this corner here. The limit of the slope coming from the left is not going to match the limit of the slope coming from the right. And since those two limits of slopes won't agree, then this particular position is not differentiable. So we might even say something like this, that the derivative with respect to x does not exist right here. Also, because we don't really know what's happening on either end of these endpoints, on the outside of these endpoints, we might argue that the derivative doesn't exist there, but that's okay. Right now we're shifting our focus to maximum and minimum points, so where's the highest and the lowest point of the graph? And the point I'm trying to make now is that while we're used to seeing high points of a graph when the derivatives equal 0, there are other opportunities for maximum and minimum points as well. So not just here anymore and here anymore, but the endpoints of our closed interval and perhaps where the derivative does not exist, we could find a maximum or a minimum point. In this example on the right-hand side, let's just do a quick check here. Does this meet the criteria of the EVT? Well, is it a continuous function? Yes. Is it a closed function? Yes. There are no, the endpoints are closed points, and it's continuous in between. So because it is a continuous and closed function on the interval from A to B, therefore there must be an absolute maximum and an absolute minimum on this interval. Now again, these absolute values can occur either at the endpoints or when the derivative is equal to 0 or when the derivative does not exist. So there are technically an infinite number of x points between A and B, but if we're looking for the absolute minimum or absolute maximum value, we really only have 6 points to investigate: A, P, Q, R, S, and B, because that's where our derivatives equal 0, or where an endpoint occurs, or where the derivative is undefined. So as far as our maximum points go, looks like we've got two of them at the same position. The largest y coordinate, the maximum point, occurs here at Q and R. I'm sorry, Q and S. And as far as our absolute minimum goes, it looks like that occurs here at point P. Now another term that we use instead of absolute max or absolute minimum are local maximum and local minimum points. And those are other high points and low points of the graph within a smaller window. For example, if I only focused on this portion of the graph and not the entire interval, then we would say that a maximum occurs at a comma f of a. If I had focused my attention to this window here or this window here, then we would have found local minimums there as well at R and f of R, along with B, f of B. Again, the entire interval exists from A to B, so we do need to consider the entire interval when looking for the absolute maximum and the absolute minimum, but as far as local max and local mins go, we can look just in smaller windows surrounding points. Now conveniently, we have a name for all of the points that have a derivative that's equal to 0, a derivative that doesn't exist, or the, well, I should say not the endpoints, because those are something separate. But when the derivative is equal to 0, or when the derivative does not exist, we call those critical points. And so on a closed interval with respect to calculus, critical points are used often to identify our maximum and minimum points. But they don't always generate a maximum or a minimum. Here's an example where this particular function will generate a derivative that's equal to 0 at this point, but clearly that's not a maximum or a minimum point. We would still call this a critical point. This is definitely a critical point, but it does not produce a maximum or a minimum. Similarly, here's a function that would pass the vertical line test on its definition, but this particular point right here produces a derivative that does not exist. It's still considered a critical point, but that critical point does not generate a maximum or a minimum value. If this was a function on a closed interval, we would have to look at the endpoints in addition to the critical points in order to locate our absolute maximum or absolute minimum points. So for the last examples in the video, certainly we could answer these questions. We could find the extreme values based on a graph, but let's see if we can do this without a graph. Find the absolute max and absolute min values on the following functions. So for part A, I'm going to check the EVT first before I get started. This will guarantee that we have an absolute max and minimum. So my question is, the interval closed? Well, certainly we're told only to investigate this function on x values between -2 and +2. So yes, this is closed. Is the function continuous? Well, remember what we're looking for are any values between -2 and 2 that would violate the domain of this function, and certainly there's no problem there. This is a polynomial, so it's always defined for function or for x values that are real numbers. So this is continuous. So does it pass the EVT? Yes, it does. So there will be an absolute maximum point and an absolute minimum point in this function. What we need to do are check the endpoints of the interval, and we also need to check the critical points. And critical points, of course, are where the derivative is equal to 0 or where the derivative doesn't exist. So endpoints, let's do that first. Those are going to be easy. Endpoints occur at -2 and endpoints occur at +2. So the function value, f of x, notice I'm not looking at the derivative yet because I want to find the maximum or minimum value for the function itself, the highest point, the largest y value. So we're going to evaluate f of x at -2, and that would be -2 to the 4th power minus 2 times -2 cubed. So -2 times itself 4 times is 16 minus 2 times, now -2 times itself 3 times is -8. So that would be 16 plus 16. We've got a y value of 32. That's a pretty large y value. Let's see what happens with the others. Now at the other endpoint, f evaluated at positive 2, well, that gives me 2 to the 4th power minus 2 times 2 to the 3rd power. And again, we get 16 here minus 2 times 8. That ends up being 0. So at the ends of the graph within this interval, we've got a coordinate negative 2 comma 32, and we have a value of 2 comma 0. So again, I don't really know what this graph looks like, but at negative 2 on the x-axis, we got a y value of negative 32, and at positive 2 on the x-axis, we've got a y value of 0. That's what we know is happening at the end. As far as our critical points go, the critical points occur when the derivative is equal to 0. So let's go ahead and find the derivative. The derivative of this one's easy to compute. 4x to the 3rd minus 6x squared. And so what we're worried about is when this equals 0 or when it doesn't exist. Now, this derivative is also a polynomial, so I know that it exists for all real number x's. So I don't have to worry about any critical points that do not exist. But I am worried about when do the critical points equal 0. So I'm just going to factor this. There's a common 2 and an x squared. So we'll leave this as 2x minus 3. And as I continue to solve, when does this derivative function equal 0? Well, that occurs when x itself is equal to 0 based on this factor, or when x is equal to a positive 3/2 based on this factor. So those are the other two positions where an absolute maximum or minimum might occur. So let's find out what happens with them. If we evaluate the function at 0, we get 0 to the 4th power minus 2 times 0 to the 3rd power. Well, that math is easy. We get an end result of 0. And again, another point at 0, 0, the same y value that we saw before. And then lastly, the other critical point was at 3/2. So 3/2 is equal to 3/2 to the 4th power minus 2 times 3/2 to the 3rd power. And I'm going to use my calculator here. I'm not going to use the graphing portion of it, but I will use a calculator just to simplify the math. And there we go, 3/2 to the 4th power minus 2 times 3/2 to the 3rd power. And the calculator tells me that's negative 27/16. If the decimal would help, that's negative 1.6875. Negative 27/16. So we have a coordinate at 3/2 and a y coordinate of negative 27/16. Now, again, using the extreme value theorem, we're saying that the extreme values will occur at either the endpoints that we've identified here, or they will occur where the critical points are 0 or do not exist. Well, these 4 points generate the positions for our potential extreme values, and as it looks to me, negative 2 comma 32, that should have been a positive 32. I don't know what I was thinking back then. Positive 32 up here. So I'm sorry if I misled you way back then. This point here looks like it's the highest, the largest y value, the highest point in the graph. So I'm going to call this one our absolute max. And then the lowest y value occurs over here, and I'm going to call this one our absolute minimum point. We can confirm this with a graph. I'm actually going to use Desmos to do that. Here on Desmos, it's pretty simple to create an equation or a graph, but it's also really easy to restrict the domain. So I'm going to zoom here and adjust this zoom just a little bit, and you can see the behavior of this graph. On that domain from negative 2 to positive 2, the features that we sort of just described are indeed true. At negative 2 comma 32 up here off the screen a little bit, that's our absolute maximum point. And then this guy right here at an x value of 3/2 or 1.5 has our minimum y value of negative 1.6875. And of course, Desmos rounded that here, but we know the true answer because we did the math. Now, I'm not going to walk through part B. I would like for you to try that on your own. But if you pause the video now and resume playback in a moment, I'll share with you my approach. So part B, this function on this interval, see if you can identify the extreme values for it.